Imagine you're running a lemonade stand and you need to give customers exact change. Today's problem challenges us to do just that. Can you always give change? Take a moment, what would you do to make sure you never run out of the right bills? Alright, let's dive into the lemonade change problem. You are a lemonade stand owner, and each glass of lemonade costs $5. Customers come one by one, paying with either a $5 bill, a $10 bill, or a $20 bill. Your job is to determine if you can always provide the correct change to every customer. If a customer pays with a $5 bill, you don't need to give them any change. If they pay with a $10 bill, you must give them $5 back. And if they pay with a $20 bill, you must give them $15 back. This $15 can be one $10 bill and one $5 bill, or it could be three $5 bills. You start with no money in your cash register. The input to our problem is a list of numbers, representing the bills each customer pays with, in the order they arrive. The output should be simply true if you can successfully give change to everyone, or false if at any point you cannot. Let's look at an example. Suppose the bills are 5, 5, 5, 10, 20. The first customer pays with $5. You take the 5, and now you have one $5 bill. The second customer pays with $5. You take it, now you have two $5 bills. The third customer pays with $5. You take it, now you have three $5 bills. The fourth customer pays with $10. You need to give them $5 change. You have three $5 bills, so you give one back. Now you have two $5 bills and one $10 bill. Finally, the fifth customer pays with $20. You need to give them $15 change. You can give them a $10 bill and a $5 bill. You have one $10 bill and two $5 bills, so you give one of each. Now you have one $5 bill. Since you successfully gave change to everyone, the answer is true. What makes this tricky is that you want to always have enough of the right denominations to make change. You can't just throw away money, you have to use the bills you have. The list of bills can be up to 10,000 customers long, and each bill will always be $5, $10, or $20. The obvious thing to try first, when faced with choices, is to explore every possible choice. This is often called a brute force approach. For our lemonade stand, when a customer pays with a $20 bill and we need to give $15 change, we have two options: either give one $10 bill and one $5 bill, or give three $5 bills. A brute force strategy would try both of these options. It would essentially ask, if I choose to give change this way, can I still successfully give change to all future customers? If one path fails, it would backtrack and try the other path. This would involve a process called recursion, where our function calls itself for each customer, keeping track of the different combinations of bills we have. For instance, if a customer pays with $20 and we have both a 10 and a 5, and also three 5s, the brute force method would explore what happens if we use the 10 and the 5, and then separately explore what happens if we use three 5s. This can become very slow because we might end up recalculating the same scenarios many times. Imagine you're at customer number 50, and you have certain bills in your register. The brute force approach might reach this exact same state of bills at customer 50 through many different sequences of earlier transactions. Each time, it would restart the calculations from scratch for the remaining customers, even though it's already figured out if that state is solvable. This leads to a massive amount of redundant work. In the worst case, if we have many $20 bills and many choices for change, the number of possibilities can grow exponentially, like 2 multiplied by itself many times, for the number of $20 bills. This means the time it takes can quickly become unmanageable as the number of customers grows. The space complexity, which is how much memory we use, would be proportional to the number of customers, as each recursive call adds to the call stack, essentially remembering each decision point. The key insight to solving this problem efficiently is to be greedy with our change. What does greedy mean here? It means that whenever we have a choice for giving change, we should always make the choice that leaves us with the most flexible bills for future transactions. Specifically, $5 bills are the most versatile because they can be used to make change for both $10 and $20 bills. $10 bills are less versatile because they can only be used as part of $15 change for a $20 bill, and cannot be broken down to give $5 change. So, when we need to give $15 change for a $20 bill, and we have both a $10 bill and a $5 bill, and we also have three $5 bills, we should prioritize giving out the $10 bill and one $5 bill. This saves our precious $5 bills for later, in case we need them for a $10 customer or another $20 customer who can only be helped with three $5 bills. Let's walk through the optimized approach. We'll need to keep track of how many $5 bills and how many $10 bills we currently have. We'll declare two counters, one for our $5 bills, let's call it 5s, and one for our $10 bills, called 10s. Both start at 0, because we begin with no money. Then, we go through each customer's bill, one by one. If the customer pays with a $5 bill, it's simple, we just add it to our 5s count. We don't need to give change. If the customer pays with a $10 bill, we need to give them $5 change. We check if we have any $5 bills. If 5s is 0, meaning we have number $5 bills, we can't make change, so we immediately know we'll fail, and we return false. Otherwise, we use one $5 bill, so we subtract 1 from 5s, and we add the $10 bill to our tens count. Now, the trickiest part, if the customer pays with a $20 bill, we need to give them $15 change. Here's where our greedy strategy comes in. We first try to give them a $10 bill and a $5 bill, because this saves more of our $5 bills. So, we check if we have at least one $10 bill and at least one $5 bill. If we do, we use them, we subtract 1 from 10s and subtract 1 from 5s. We don't need to track $20 bills we receive because they are only useful for change, and we've already accounted for the change we gave out. If we don't have a $10 bill and a $5 bill combination, our next best option is to give 3 $5 bills. So, we check if we have at least 3 $5 bills. If 5s is 3 or more, we use them, we subtract 3 from 5s. If neither of these options is possible, meaning we don't have the correct change, then we return false. If we successfully process all customers without returning false at any point, it means we could always give change, so we return true at the end. Let's trace this optimal greedy algorithm with our example. Bills are 5, 5, 5, 10, 20. We start with our counters, 5s is 0, 10s is 0. First customer pays with a $5 bill. This is a $5 bill. So, we increment 5s. Now, 5s is 1, 10s is 0. Second customer pays with a $5 bill. This is a $5 bill. We increment 5s. Now, 5s is 2, 10s is 0. Third customer pays with a $5 bill. This is a $5 bill. We increment 5s. Now, 5s is 3, 10s is 0. Fourth customer pays with a $10 bill. We need to give $5 change. We check if 5s is greater than 0. Yes, 5s is 3. So, we decrement 5s by 1 and increment 10s by 1. Now, 5s is 2, 10s is 1. Fifth customer pays with a $20 bill. We need to give $15 change. Our greedy strategy says to first try giving a 10 and a 5. We check if 10s is greater than 0 and 5s is greater than 0. Yes, 10s is 1 and 5s is 2. So, we decrement 10s by 1 and decrement 5s by 1. Now, 5s is 1, 10s is 0. We have successfully processed all customers. Since we never returned false, we return true. And there's our final result for the example input of 5, 5, 5, 10, 20, true. The algorithm successfully determined that we can always provide change to every customer because our greedy choices ensured we kept the most flexible bills available. You'll spot this greedy pattern when you're making a sequence of decisions, and at each step, there's a clear best local choice that doesn't negatively impact future decisions. Specifically, if you have multiple options for change and one option uses up more versatile resources, like our $5 bills, while another uses less versatile ones, the greedy choice is often to preserve the more versatile resource. This optimal solution runs in linear time, meaning its speed scales directly with the number of customers. It uses constant space, as we only need 2 counters regardless of how many customers there are. Try solving another problem like activity selection to practice this same greedy pattern. If you found this explanation helpful, please subscribe for more DSA deep dives.